All right, hey everyone. Good morning. Thanks for coming in early. So the purpose of this workshop is just gonna be just to help you sort of think about how you can approach this problem or just sort of ways you can think about artificial intelligence, machine learning. Before I begin, I do want to here, just on behalf of HackMelbourne, I want to acknowledge the traditional owners on which the land that we're meeting on today and the Wurundjeri people of the Kulin Nation. I would like to pay my respect to the elders past and present and emerging. So who am I? Well, I'm Yupin. I'm currently the outgoing president and the outgoing treasurer of outgoing president of HackMelbourne, outgoing treasurer of Women in Tech. I am currently in my final year of my bachelor's, and after this I'll be done. So moving on, I just want to give a bit of expectations as to what this workshop's going to be about. Feel free. So this is in the context for people online. This is for the context of a hackathon. If you want to listen along, feel free to. If you don't want to, that's perfectly fine. Feel free to just carry on discussions or do whatever you want. What this workshop will be about is to sort of touch on some possible algorithms, or essentially what algorithms are to begin with. And then it's not to say that you have to implement these algorithms to win. So please think about it, because some of these are very hard to implement, to be honest. But the point is to get you thinking about like algorithms and autonomous agents. And we'll start from the very basics, because I'm aware that some people here may not even be studying computing. That's perfectly fine. We'll start from the basics, we'll work our way up, and we'll hit some pretty advanced algorithms. And those are kind of stuff you'll just have to research about. All right. So just to start, let's talk about the game itself, Battleships. The game is, well, pretty simple, I think. So both teams will get to set up their own boards. You get to put specific ships with specific layouts. So you can only have certain ships with, let's say, size of 2, some are size of 3. You can't have like a 5x4 ship because that's kind of weird. Each team will get to shoot a missile on each turn. So that's sort of your actionable. And the last team standing, so if your ships all haven't sunk, you've essentially won. So that's sort of the bare bone mechanics of the game. There are some different versions online, but I believe this is sort of what we're going off of. And so let's just start with thinking about algorithms. What basically is an algorithm to begin with, right? So an algorithm, all it is just a step-by-step procedure, and you're trying to solve a problem. So algorithms are everywhere, and you need to start thinking about how you approach a problem in order to create the generalized structure for the problem. So in this case, we're talking about how you would create a general procedure to play battleships, but just algorithms in general. What it is that you're thinking of a general way to solve something. What is the general procedure for you to do something? And so they're everywhere, especially if you do math and engineering. You would have already seen quite a few algorithms, especially the ones where you have to work out by hand. You even see them in art. For example, if you want to recreate like a drawing, you see something nice and you want to draw it out. That generative process is now something that's very popular now. If you see those generative networks and recreation of arts. So we've somehow managed to turn drawing into an algorithm. And that's kind of where we are at the moment. What we want to do is create a procedure to play battleships. So let's start with sort of how you even begin to come up with your steps and everything. So if you think about a procedure, you would have stuff like actions, what can you do, and states, what do you know? So there are many ways to represent this, especially in Python as well. There is a reason why a lot of subjects that you hear being passed around in computing, they will sound something like algorithms and data structure, or design of like algorithms. And if you look into the syllabus, they're all covered with data structures. And that's because that is how you represent information. So it is important that you know what actions you can take and how you should store them. Generally speaking, you have sort of the concrete data types. So stuff like your primitive types, integer strings, maybe your arrays. And then you can get into some more abstract stuff, sort of like your queues, your stacks, that sort of thing. And what you want to do is sort of take those states, right? So in this specific example, what we're doing is you're being thrown at all these states, right? So your board, your player, sort of like what happened before, what's gonna happen next, those sort of stuff. You take those states, optionally, you can make them more efficient. So something that I've brought up during Decoded was in chess, you have to think about the possible states you can generate in, especially in a like an autonomous agent, because what you're trying to do is sort of to find the possibilities and pick the best option. And because you're generating so many possibilities, you have to think about how, like, what each state might represent. If it's a whole dictionary and you're generating billions of them, your computer might struggle handling stuff like that. So there are ways you can make it smaller. In chess, there's something called the Venn notation, where it's like you take a board and turn it into just a small string where it tells you everything you need to know about whose round it is, how many turns it ends, who has what on which position, en passant, all that kind of stuff. And you can do one better by turning it into a bit representation. So that's called a bit board. And here, you can also try doing something like that, where you make it more and more efficient so that when you explore your states, it's less hard on your computer, which means it runs way faster, which is very important because you do not want your program to be stuck on an action and just not decided anything, because you technically lost. You didn't do anything. So now that you have all your information, you decide on an action. And so you can think of it as sort of the states are like where you've shot, and an action is like shooting a square. That's what we're doing here. And let's talk about some baselines. You've already seen in the code, in the Battleship code, that we've introduced sort of a random agent, and that is pretty much as low as you can go. If your agent cannot beat random, you probably should have done it in the first place. But a random agent just does whatever it wants randomly, right? No regard of heuristics, no regard of like any new information being taken on by your agent. So earlier I said heuristic. What is that? Heuristic is sort of the approach in your procedure. So you think of an algorithm as a procedure, right? Heuristic is sort of your general approach so that you hit some kind of approximation. And so we can do slightly better by using heuristics. We can make it pseudo-random so that it's kind of random, but every time you observe a hit, you can do something about it. You can act on it, right? So acting on that information can guide you into winning, and that could be a heuristic. So earlier I've said that baseline is sort of the lowest you can go. And in computer science, being able to compare algorithms is very important. So I'm just going to bring this up here in case you want to know about sort of comparing. It's going to be really useful if you study computer science. And even if you don't, it's really useful if you want to know if your computer can run the algorithm to begin with. If you're struggling with something that has a pretty high complexity and you introduce a new algorithm that's even more complex, well, how do you know one is more complex to begin with? And if you now do know, you'll know whether or not you can run it, right? So I'll be honest, the advanced ones get way too difficult to calculate by hand. Just Google it or like literally run it, and you know, like if it takes minutes or like hours, you'll know if it's too complex for the competition. And just some intuition about how you would compare. So you would want to think about how often you work with your states. So for example, if for each state, you're just computing something, right? That is just like for every item, you'd be doing something. So you can think of it as like a function that does something n times, O of n. That's kind of what it is. And then, you know, if you want to compare each state against other states, then you have like n squared, and then it goes on and on. And later on, the algorithms get more and more complex. You can't really compare them this way too intuitively. But this is sort of what you are expected if you're doing complexity analysis. Important to think about is your state generation and your state computation. That will sort of guide you into what your complexity might be like. And I want to mention earlier, I've put here model analysis. So like model evaluations. That is different to complexity analysis. Just to bring that up, model analysis is more like a machine learning thing, where you're talking about like whether or not your model overfits or like it generalizes well, the biases, the variance. So that is something you need to keep in mind if you're using those sort of techniques or those kind of study or research to improve your heuristic. And yeah, so let's try our first semi-decent algorithm. Let's think like a human and we approach our algorithm using like human thinking. So let me just take a guess at how I might play the game. If you put the game Battleships in front of me, what I'm gonna do is I'm just gonna throw random shots until I find something. And then at that point, I'm gonna try and look around it to see if I can sink that ship. There's no point jumping into another ship if I can sink this one first, right? Because the goal of the game is to sink the ships of your opponent's team as fast as you can, because you do it before they do it, right? So if you think of this, I kind of have like two modes here. I'm hunting down for a ship. I'm looking for one, I'm trying to sink it. And then I'm actually trying to sink it. So the target mode. So there is like some studies done on this. And you can think of it as hunting and targeting modes. So now, instead of randomly picking squares, you now sort of have two modes where you can approach this. And you can even improve it some more because earlier I said random. Random searching, well, if you've ever done anything computer science related, you know, there's a whole bunch of like resources and literature on searching to begin with. What if there is a more efficient search method? And what if it doesn't have to be every single square? Can you somehow prove that there are certain search configurations, not necessarily algorithms? Let's say you do search it randomly. Are there any specific configurations that will lead you to a more optimal search, or if not, the most optimal search? For example, instead of searching a square from left to right, and then like you go down the entire array, what if you search like every two squares? Will that make your algorithm more efficient? Will it make it less efficient? Or the more gaps you give, will it give you a better search space? So those are some things you can keep in mind. And to do one that's even better, you could even sort of apply a heat map. So think of like a distribution of probabilities across like your map. So instead of just searching like every two square, every three square, what if there are zones where you feel like your opponents were more likely to put like their ships? So that's something you can keep in mind. You can have a look here. So some people have already tried looking into how you might use heat maps and like whatever I said earlier, hunting and targeting. So you have to think about updating probabilities. So what is the probability of ships around the target if you've missed? Is it higher or lower? And what happens if you hit a ship? So being able to update your algorithm to properly take on these new updated beliefs is going to be very, very important. And here's just like a little analysis of like sort of which methods this person found to be pretty effective. Some seem to be quicker than others. Some seem to be like more computationally expensive. That's up to you to figure out which one's best, and it's up to you which one you can implement because they're not all necessarily very straightforward. Right. And then talking about probabilities, this one comes up pretty often. If you ever do anything AI related, this one will show up. So there's this theorem in probability, the Bayes theorem, where it's all it is essentially, let's say I have some prior knowledge. For example, I think today is sunny. It's not gonna rain, right? So the probability of rain is low. That is my assumption, which is my prior. And then as I walk to uni, I'm gonna see the sun's out. No one's wearing like no one's holding an umbrella. There's no raincoats around. And so that's the model giving me evidence, right? I'm seeing the world and it's giving me evidences of, oh, it's not raining. Issue is, we know Melbourne's weather is pretty crap and it's not necessarily going to stay that way for the next 5 minutes. So that's why it is a likelihood of evidence because the model may be wrong. So if I see people without umbrellas, it does not mean it's not raining. So it's a likelihood that it's not raining rather than just saying, oh, people aren't holding umbrellas, it's definitely not raining. So using my prior beliefs about the weather, I will update them using the likelihood of it with my given observation to develop this new probability called the posterior. And so the evidence is sort of like just adjusting it and normalizing. You don't really have to worry about it. Using Bayes' theory, you can implement certain search algorithms where you develop a prior. So the entire search space has some kind of probability to begin with. And as you search, you update your beliefs as to where the other ships may be. If you find a couple cluster in like the left side, it may be the case where more of them happen to appear on the right side now. So that's something you have to keep in mind. Bayesian search theory is something that's actually used in real life when looking for missing ships. So implementing this in battleships is probably also very intuitive. Yep. So it's all about searching and updating belief. That's all. Right. And then now I'm gonna touch a bit more on slightly advanced algorithms. Feel free to just not listen to this if you don't know what's going on, but I'll try and keep everyone in touch. The first one that this isn't really non-deterministic. This is non-deterministic, but it's in an observable environment. What I mean by that is that the outcome isn't deterministically evaluated. There isn't some set algorithm. It's more probabilistic, but you can only run this algorithm if you can see the enemy ship. That doesn't really work. It's not really good for us, but we can extend it in a way. So let's start with Monte Carlo tree search. This is a really useful one when it comes to sort of just like, let's say if you don't want to develop the general algorithm and you want to leave it to more so like the amount of times you win. So essentially your win rate. Win rates are very important here. And what I mean by that is that the whole algorithm relies on selecting nodes from a tree. So imagine each node as like your board, each circle here. It could be sort of like where you've struck and where the enemy ships may be at. So shooting at another square is going to give you a new state, right? And then whether you hit or miss is going to develop more states. So you start by selecting a node where you have not explored something. You want to expand it. And the way you test whether it's good or not is through simulation. So you could maybe make it shoot random shots. And then like the issue with here is you have to know whether it wins or loses, which is why it doesn't really work because you don't know where the enemy, you can't validate it since you don't have enemy ship like vectors or like where it's at. But if you do know, you can simulate it and know whether your moves are good or not. And you can back propagate upwards to tell your tree whether or not this is a good move to begin with. So think of it as like telling the rest of the tree that, oh, by playing here, I have a higher win rate. So we can do that. So selection is about finding the non-terminal nodes and you expand. Expansion itself is about using a good policy because you technically can expand in many ways. That's sort of like how you want to shoot. There is this thing called like the upper confidence bound or something like that. And that's sort of like, you can play a trade-off, right? You can either play risky moves or play safe moves. And there are like ratios where you can balance that. And you simulate it to check it if it's like invalidate or whether it's like an actual state. And then you back propagate. That's all this is. We can push this slightly more. This doesn't really work for us because of the, like what I said earlier. We can make a Monte Carlo tree search, which means we have this concept where we are in tree and out of tree. When I say in tree, it means we're in this Monte Carlo tree search. And when I say out of tree, it means we're just using like some uniform distribution or like some random distribution, right? So let's say I'm at some node. I don't know what the actual outcome is. So let me throw some random shots and then it's going to give me an outcome. So maybe I missed. So in my Monte Carlo tree search now, when I generate this new node, I'm going to say, hey, the payoff of shooting at this specific square for this specific match is bad. So I have a terrible win rate by shooting at this square. And if you can do that by switching in and out between what you have explored and what you've never explored, you can sort of aggregate through a bunch of games. And the model will kind of start to understand where are like certain good spots to hit and where are spots where people may never put their stuff. So that is a possible way of doing it. Another way is using Markovian style of doing things. So this is a Markov decision process. Each state is sort of like the state of your board, and every state has a set of actions. You can take a state, perform an action on it, and you'll need something called a transition model. That's sort of like, well, the probability of reaching the next state if you apply some kind of action to the state before. So what is the probability essentially? And so this is kind of similar to the Monte Carlo tree search, where you still need to know the probability of like hitting or missing, and you do not know that. So you can turn this into a partially observable Markov decision process, POMDP, and you can look this up if you want, but it's sort of just taking this and you add on one more, like, so earlier I talked about the transition model. Now you add on something called the observation model, where it's sort of like the probability of observing. So you're adding more layers of probability just so that you can check against yourself later. That is what that is. We're gonna start reaching into difficult algorithms to implement, but these are kind of useful just to know anyway. Now, I've talked about Monte Carlo tree search earlier. This is Markov decision process. What if you can combine the both? So there is something called a Markov chain Monte Carlo. If you want to somehow combine the both using, so it's based on this theory of the big number law. So Monte Carlo is good at simulating, so you can generate lots of sample. And Markov chain is like something you would use for probabilistic search anyway. So, or like just probabilistic inferences. So if you can somehow combine the two, you can also create a very powerful search to guide sort of your agent into shooting your missile in certain places. That's what that is. I won't touch on the specific algorithm. You can also try using neural networks if you're adventurous. So I'll quickly talk about the basics and then the specific algorithm that I've seen that was used before. And neural networks is a very big topic, especially now if you're into like ChatGPT and stuff. There's many different kinds. You may have heard of single layer feed forward, multi-layer feed forward, recurrent networks, fully recurrent, competitive networks, or like some kind of variance. There's so many different kinds. But what it is someone essentially wanted to mimic like a neuron. And they found that, well, if you have some input, you have weights that adjusted. So here it's like denoted W0, W1. And every weight, when it enters a node, it is biased in some way. Then if you take that and you push it through some kind of function, it's called an activation function. It would give you some kind of output. So here you can kind of see how you could adjust your weights and biases to produce the output that you want. And the activation function is here because when you move on to something that's with more than one neuron, so like especially if you have multiple hidden layers, you want the activation function that to give you non-linearity, especially if like, let's say in more like machine learning context, you will want that non-linearity in order to like perform certain things, right? So at the very end, we'll get some kind of output. That is not all we want though, because we want our model or our agent to learn. And the very essence of neural networks is this feature called the backpropagation. Similar to what I've said about Monte Carlo, if you backprop from the output, so you compare the output to the error, you find that difference, you can backpropagate across your entire network to sort of like get it to adjust accordingly. That is the very essence of neural networks and how it learns, basically. And there is this advanced algorithm called NEAT. Forgot what it's called, Neuro Evolutional Augmenting Topology. It's essentially trying to have an evolutionary take on creating like neural networks. So if you think about evolution, right, you start with like the brain, or here it's called the genome. And so in your genome, you have some very basic neural network. Let's say it's just the input and output. And as you mutate, as you augment, and as you cross over, so meaning you find good nodes, you're generating more and more mutations of different layers, different number of nodes, different weights and biases. And so that's sort of just the internals within the genotype. And it is expressed in something we see called a phenotype, and that's like the network. So using that, you could sort of get it to train and play it by itself over and over again until it finds like a very good neural network structure that can defeat basically anything. A very big issue with this is I have a feeling you won't be able to train this in time, but it is still worth a read or like worth a try if you want to try something neural network related. And yeah, so the very last thing I want to cover is the second last thing is earlier I've mentioned this notion of like a neural network and hidden layers. So without the hidden layers, it's just like an artificial neural network, right? You have your basic input outputs, but as you add more hidden layers in between and you reach like some big amount, it's called a deep neural network. And when back propagating, if you can introduce some kind of reinforcement, you may have heard of this before, but it's called reinforcement learning. So by implementing more layers and by giving it rewards, so rewarding specific nodes for doing good things, you can start to speed up and like improve that sort of learning and associativity. And so these specific algorithms for doing this, that's quite a lot. And this is very much in like current research already. And there are currently available algorithms you can just plug and use. One big one is probably Q policy. And it's sort of just how you would update your weights and biases. So like how fast you want it to update and just basically how well it can capture a good Battleship playing model. So this is something you could try as well. It's within the field of like TD learning, temporal difference. And similar to NEAT, this will likely be very, very, very difficult to implement, but also worth a read if you're interested in stuff like this. And the last thing I want to mention is I've talked about quite a few different algorithms. One aspect that I didn't bring up is on the ethics and social engineering side of things. I've just reviewed quite a few decent ways of doing things. There is a field, I can't think of it off the top of my head right now, but it's like adversarial related stuff. So adversarial AI, adversarial machine learning, where you take advantage of known methods and you mess with people. So if you know that people are gonna, let's say, generate a heat map where it's like evenly distributed, if you stuck all your ships in a corner, it's likely to get missed. So there are ways where you can mess with people's algorithms or like reverse engineer and try and break theirs. That is something you can look into as well. And yeah, that is essentially it from me. Are there any questions or like just things you want to know? If not, I'll be here anyways, and later my committee will be around if you want to ask any questions. But just for the sake of the recording, I might just stop here. Thank you so much. Appreciate it. And yeah, all the best for the hackathon. Thank you.